All right, let's look at notes for 7.2a. We are talking about volume by the disk method. But first, let's review area of a shaded region. We talked about how we can use this concept of adding up infinite number of rectangles to get the area, the exact area of a shaded region. So let's say we have the shaded region here created by or bounded by y equals square root of x, y equals 0, which is the x-axis, x equals 0, vertical line x equals 0, and vertical line x equals 4. And if we put it into integral notation, area will be represented as the definite integral from a to b, so left bound to right bound, f of x dx. So this f of x represents the height component of this rectangle, and the dx represents the width component of this rectangle. So we see the height and the width portions in this definite integral formula. So if we wanted to adjust, and if we want to solve this problem to set it up, we would, for this particular problem, we would say area is a definite integral from 0 to 4, square root of x, because that's the equation of this curve, dx. So square root of x represents the height of this rectangle for each of the respective x values. Okay. Now we're going to take this area, this concept of area, and we're going to apply it to volume. So let's look at that. We're still going to start off with same shaded region, still the same equation. We're still going to draw a rectangle. But now this rectangle is no longer going to represent the height of a rectangle. This figure that we just drew will now represent the radius of cylinders. So if you can imagine, we have this shaded region, but we also have this axis of revolution where we're taking this rectangle, the shaded region, and we're revolving it 360 degrees all the way around this center, this axis of revolution. So when we do that, we're going to come up with an object, a three-dimensional object that looks like this. Okay, kind of a bowl that is opening up sideways. And let's look at, and so rather than adding up infinite number of rectangles, now this object is created by adding infinite numbers of circular cylinders. And you can see that the cylinder here is represented in this picture a little bit better. So let's talk about the different parts of this cylinder. Okay. So with the cylinder, you see that this circular region, we see that the distance from the center to the top of this cylinder represents the radius. Okay. So that is why when we're looking at, when we drew this rectangle, this is no longer the height of a rectangle. This is, the height of a rectangle. This will now represent the radius of the circular region. So you can see a little bit better after everything's been rotated. You can see why this is represented by r of x, why this is the radius. Okay, so volume has an area component and a width component. So if you look at this, this is a circle. So the area of a circle is given by the formula a is equal to pi r squared. So to adapt to this particular picture, our area is pi r of x squared, because r of x is now representing the radius for this particular situation. And dx is the width of this circular disk. So if we talk about the volume, volume has an area portion, so we're adding up these infinite circular disks, so that's why we have this pi r squared in the formula, and then this dx gives us that third dimension. Okay. There are two ways that we can set up our formula. One is if we have a horizontal axis of revolution, which is what we saw from above here. If we have a horizontal axis of revolution, then we're always going to be drawing our rectangle or our radius from the axis to the curve. Okay? And if we have these vertical radius, these vertical rectangles, then we're always going to be plugging everything in terms of x. Our bounds are in terms of x. Our function is in terms of x. And we pull the pi out in front because pi is a constant, so it kind of gives us, we can pull something out that's not going to affect our formula. And after we find the integral, then we can attach that pi to our final answer. So usually you're going to see that pi outside of the interval, outside the integral sign. Okay. However, if we're rotating about a vertical axis of revolution, a vertical line, then we're going to have horizontal rectangles. So if we have horizontal rectangles, then everything is in terms of y. It'll be right minus left, and our bounds will be in terms of y as well. Okay, so here are the steps that we're going to take on the back page when finding volume using this method. First, we're going to graph our equation, and we're going to shade the enclosed region. Something that we have to be careful about is sometimes you're given a lot of different equations and a lot of different lines. We have to make sure that each of the lines and graphs that's provided in the problem, they all have to contribute as boundaries for your shaded region. So if you shade a region and you see that that shaded region does not include one of the lines that was given to you or curves that's given to you, then you have to go back and think about where that shaded region is. Next, we have to draw the axis of revolution using dashed lines. Okay, again, if it's horizontal axis, we use top-bottom method. If vertical, then we use right minus left. And then starting on the axis, okay, we usually draw the axis using a dashed line. Starting on the axis, you're gonna draw to the radius, or draw to the curve, and that will represent the radius. And make sure that when you draw your radius, it always has to include this axis of revolution. Okay, you can't have a radius that doesn't. You can't draw a radius if it doesn't include the center of that object. Okay. Again, we can double check to make sure that we have the correct formula, or we're using top-bottom, or we're using right-left method. Next, we set our equation equal to each other if needed to find those intersecting endpoints, to find our boundaries, to find our bounds, so we can plug into our formula. And finally, plug values into the definite integral to find volume, and usually we leave pi in our solution.